Errors in computation. We will start this video by talking about errors in computation, and then we will end by talking about uncertainty analysis. And these two topics are easily confused. When we talk about errors in computation, we're saying that we know exactly what the real answer is, and therefore we know how far we're off our calculation was. More realistically is perhaps the uncertainty analysis. When we don't actually know the exact answer, we have an answer that we've calculated, and we only have sort of this statistically derived uncertainty that bounds how much that answer could be off by. So let's get into this. Errors in computation. Let's start by talking about really the three types of errors that we can encounter. The first is called a truncation error. Very often when we're formulating codes or algorithms, we will make approximations in them. One very common one, we have potentially a square root, and we know we have the binomial approximation where if this x value is less than 1, if the absolute value of that is less than 1, we can approximate that square root just as 1 over x divided by 2. Other times we will approximate derivatives using something called finite differences. And this really is just sort of a rise divided by run approximation of slope, which is our derivative. But that obviously is not exact. And so if we build these things into our algorithms, we know we're also introducing error, and that's called a truncation error. The next type of error is a round-off error. And this happens anytime we're storing a number that actually has more digits than we can possibly store. Some great examples are pi. Our computer can only store that to, 16 digits or so. The constant e, square root of 3, other types of irrational numbers. Other times that this can come up, go into MATLAB and type in 0.3 divided by 0.1. That should give us an answer of 3. And then if we subtract 3, we should get 0, but this is actually the answer that we get. And that's because with floating point arithmetic, these numbers really can't be stored exactly. And so we get these small errors. That's a round-off error. And of course, the last, and a lot of textbooks miss this one, is human error. And this actually comes up probably more often and is more significant. And maybe we're deriving something on paper and we do something like 1 + 1 = 3. Happens to me all the time. It happens to the best of us. And we have to recognize that as a source of error. Just because your computer program gives the wrong answer does not necessarily mean it was the computer's fault. We have to look at what we do with our codes as well. Quantifying error. One very common way that we quantify our errors is just by the number of digits we write into our number. And maybe we're not even thinking about that. So for example, if we have a number 1.234, that implies that this really is the accuracy of our measurement. We really can't obtain further digits. Our measurement equipment probably had those other digits, but they were probably fluctuating around or other things were happening. And so we really only report the digits that we trust. So simply by the number of digits that are reported or number of significant figures, we get an assessment of the error. So by looking at the number of digits, there's really two rules to determine the number of significant digits. Any non-zero number is a significant digit. The confusion comes in when there's zeros. So we have to look at the application of the 0 in that number. If that 0 is doing nothing other than placing where the decimal is, we don't include it as a significant digit. Let's go ahead and go through some examples to help illustrate this. So let's say we're given this number, 1.234. Well, there's no zeros here. We have all non-zero digits, so we just count them. 1, 2, 3, 4. It looks like we have 4 significant digits. Let's look at another number here. Okay, well, we have 3 non-zero digits. So we have at least 3 significant digits, but we have 3 zeros here. Well, zeros is the one that we have to give more thought to. Now, we could look at this and think, well, maybe we have 6 significant digits. However, if we look at the application of those zeros, what we see is these zeros really aren't doing anything other than placing where this 545 is relative to the decimal. So in fact, we don't count those as significant digits here. So this has 3 significant digits. Now here's a tricky one. 32,100. How many significant digits here? Well, right away we see 3 non-zero digits. So we have at least 3 significant digits. But what about these 2 zeros? You know, this case, it's actually ambiguous. We could argue that these are doing nothing other than placing the position of 321 relative to the decimal that will be down here. However, the mere fact that we've written these and we're not using scientific notation could also tell us that those should be significant digits. So the answer here is that it's ambiguous. There's either 3 or 5 significant digits. We'd have to be told some more information to figure out whether that's 3 or 5. 0.0500. Okay, a lot of zeros here. Well, there's one non-zero, so we have at least one significant digit, but we have 4 different zeros here. Well, these first 2 are doing nothing other than placing this 5 relative to the decimal, so we're not going to count those. These last 2 zeros, we can be sure when they follow this after the decimal point that these really are reporting significant digits. So we have 3 significant digits in that number. True error. So somehow, magically, we know the exact value, and we will call that the true value. Well, we've made a measurement, we've done a calculation, and we have some kind of approximate value. Well, we take the difference between those two, that is our true error. So here's an example. We actually know the speed of light exactly simply because we've based the meter in second or some combination of that off of the speed of light. So the speed of light for us actually is exactly 299,792,458 meters per second. Well, let's say we set up an experiment that measures the speed of light, and what we measured was 299,792,445 meters per second. Question in, what is the true error of this measurement? Well, our true value is the 299,792,458 meters per second. Our approximate value that came from our experiment, 299,792,445. So we apply our definition of true error, where we have the true value and we subtract our approximate value, and we get 13 meters per second. That is our true error. Let's end this with some notes. It is very rare to actually know the true value of something because we only ever really have the approximate value. So it's rare we do this, so despite being somewhat unrealistic model, this is actually useful when we're analyzing how errors propagate through our calculations. The other thing I'll point out is that true error is really, in my opinion, not a great measurement of error because it does not convey the severity of that error. So here's an example. I'll tell you, I've just done a measurement of distance, and my error is plus or minus 1 foot. And I ask you, how accurate is that 1 foot? Well, you don't really know. Well, what if I told you I was measuring the height of a person? Well, wow, to be off by 1 foot for people that are typically in the 4 to 7 foot, that's a big error. That's horrible. However, if I was measuring the distance between galaxies and somehow, wow, I'm accurate to within 1 foot, well, that's an amazing thing. So the true error doesn't really tell us how significant that error is. Let's go on to the next, which fixes this. We have what's called the relative error. The relative error is the true error that we just discussed, but we divide that by the true value. So in a way, we've normalized it. This relative error will not have any units. And let's go through an example. So same thing again. We know the speed of light exactly. We measured it. We have the same 299,792,445. Now, what is the relative error in this measurement? Well, in the previous example, we calculated the true error, that was 13 meters per second. We will divide by the true value, and we get this 4.33 times 10 to the minus 8. Let's put that on a percent scale. Wow, our error is 0.0000433%. That's a hugely small error. So by going with the relative error, we know this is a really good experiment. We've done extraordinarily well here. So pretty good. So we'll end this with our last measurement of error. This is called approximate relative error. Remember before I mentioned it is extremely rare that we know the actual true value. So usually we only know the approximate value. So we'll just change our definition of relative error a little bit, and we'll say approximate error divided by our approximate value. So I'll end with this neat little equation, and we can be sure that quantities are correct to at least n significant digits if our approximate relative error equals this quantity here. Notice here's that n, it's in the exponent here of the 10. So neat way to figure out how many significant digits we have given the approximate relative error. Error propagation. So what is error propagation? So we have numbers that have error associated with them, and we're going to use those to do calculations. Well, if we're using numbers that we know have errors and we use those in calculations, then clearly those calculations will also have errors. So the question, or what error propagation is trying to do, is figure out how those errors trickle through our calculations. So let's start off. We have some value of x, and we put this little tilde above it, so x squiggly. This is the x value that has the error in there. So we can write this as x plus a delta x. So in this case, x, that's the true value and our true error. And so this x squiggly gives us the number that's slightly off. So now we do a calculation with that. We'll write that just generally as some function of x, the x that has the error associated with it. Well, given that that x has some error delta x, what's our error delta f? Let's look at that. Let's derive an equation for calculating how an error would propagate through some kind of equation. In this case, our equation we'll be writing as f of x. So very often when we do this sort of thing in computation, we employ Taylor series. So we're expanding our function into a Taylor series and we're expanding it about a. There's an infinite number of terms here, and it's always difficult to impossible to work with an infinite number of terms, so we will truncate this. And we'll retain only the first n plus 1 term. So here I'm just really writing the first 3 terms, and then all the other terms that exist in this infinite series, we've lumped into this r sub n term. Now, the values of these terms, they get small very, very quickly. And so we're really just going to drop these higher order terms and ignore them as if they were 0, because we're really just trying to get an estimate of this error propagating through our calculation. So we will rewrite the Taylor series. Rather than writing it about a, we're going to write it about the measured value, this x tilde or x squiggly, as I normally like to say. So here's our first 3 terms, and yes, there's a whole bunch of other terms, and we're dropping them. So we're going to bring this function, the function evaluated at our x squiggly term or x tilde, we're going to bring that over to the left. So now we have our true calculation minus the calculation that has the error in it. Well, this difference actually is our error, delta f. That's what we're trying to calculate. The other thing we'll recognize, we have x minus x squiggly, x minus x squiggly. So it's the true value minus the value that has the error in it. That actually means that those 2 terms are the error. So we can write this equation again a little bit more simply. And on the left, we just have our delta f, and we're replacing the x minus x tilde with delta x. At this point, we'll just drop all of the higher order terms, retain only this first one, And that is actually the equation we will use to calculate the error f. And yes, we're ignoring these higher order terms, but these higher order terms get small very quickly. So this is a very good calculation. So the error in f is the derivative of f evaluated at our x squiggly. That's the value of x that has the error in it. And then multiply that by the error in x that we know going into this. So this delta x is the error that's going to trickle through the calculation, and the delta f is the error after it gets through the calculation. So this was for one variable. We can generalize this to two variables, and it's always the derivative of the function divided by the parameter times the error in that parameter. And we can do this for a y. And of course, if you can see this, you can see how we could generalize this to any number of parameters. Let's do an example. Let's say we have a number that has error in it, and our number's 2, and the error is 0.05. So what's the error if we were to square that? Well, the first thing we'll do is we'll start with the definition of error. So our definition of error is the derivative of our function, evaluate that at our x value, and then we multiply that by the error. So we derive the derivative. The derivative of x squared is 2x. So it'll be 2x times the error. Now we plug in our numbers. The value of x that had the error was 2. So we bring the 2 down here. And of course, our error, 0.05, comes in here. And so we perform our calculations, we simplify, and we end up with a value of 0.2. So to repeat this, if we have x, its value is 2, but the error associated with that is 0.05, what is the error of x squared? Well, it turns out it's 0.2. Maybe we find that surprising, maybe we don't. Now we jump to uncertainty analysis. So what is uncertainty? Let's say we've measured the length of an object, or we're trying to measure the length of an object. Well, the length is sort of uncertain. There's kind of this blur at the end. Maybe you're using a ruler and your eyes aren't working so good. You can't make out the lines, and you can say, oh, I can get it to within 1/8 of an inch, but you know, it's kind of blurry to me. So we don't know the true measurement anymore. We can put a best guess somewhere at the middle of this blur, but we have this blur, and the significance of this blur is the uncertainty. So we would write a measurement like this as x plus or minus some value, and this value is quantifying the extent of the blur. So this x is, our best guess right in the middle of the blur, and then the sigma is quantifying the blur. And of course, we'll get into the normal distribution on the next slide. So that sigma is really quantifying the blur. It's called our uncertainty, and it is a statistically derived quantity. We have to use statistics now because we don't have a true value to go with. So just some notes. This is a much more realistic way to treat error because it's very rare that we actually know true values and true errors. And so we use uncertainty to predict errors in our computations before we know anything about the values. A little bit more about interpreting the uncertainty. The uncertainty is not bounding our error. So if we're saying our value is 10 plus or minus 1, that does not guarantee that our answer is somewhere between 9 and 11. Doesn't do that at all. So if we have 10 plus or minus 1, that means our 10 values right here, and plus or minus 1, we have a 68% chance that the actual value will fall between 9 and 11. There's actually a 32% chance, call that a 1/3 chance, that our number is actually less than 9 or greater than 11. And so this distribution is called the normal distribution. And when we specify sigma, we are really specifying this little distance here off the nominal value. We'll call that 1 sigma, and we can jump out 2 sigma and 3 sigma and so on. Now let's get into uncertainty analysis. Let's go with multiple parameters. We're using x, y, and z here, and each one has its own uncertainty. Remember when we say uncertainty, think blurring, think fuzzy. These are not specific values anymore. And we now want to calculate something with them. So we're using X, Y, and Z in some kind of calculation. We would like to know the uncertainty of that calculation based on the uncertainties of X, Y, and Z. So here's an equation of how we do that. And it's a little bit different than when we were talking about error. So the uncertainty squared of our calculation is the sum of a bunch of squares. And inside each of those squares, we have the derivative of our function with respect to some parameter multiplied by its uncertainty. So what's inside these parentheses looks very much like what we're using for error, except we're squaring it. We're summing all of the squares for each of these parameters and then taking the square root, and we'll get the overall uncertainty for that calculation. So when we do that, that's called propagating uncertainty. Here's a table, also providing this on the course website, of a bunch of common calculations. So in this case, X or Y and Z, these would be the things that would have uncertainty. So what would happen if you multiplied a number that had uncertainty by a constant? Well, the uncertainty of that calculation is just that constant times the uncertainty of X. And so anyway, you can go down the table, and here's a whole bunch of different calculations and how to get the uncertainty. And these were all derived from the equation presented on the previous slide. So we can use a table like that to analyze more complicated things. And so let's look at uncertainty through multiple calculations. So here's our function now, the natural log of A plus B times C. And we're saying that A, B, and C, these parameters all have uncertainty associated with them. We can look at a function like that and see that as a series of simple functions that we would find in the table on the previous slide. So for example, the first thing we might do is multiply B and C. These are both things that have uncertainty associated with them, so we will get an uncertainty associated with the product. We can go to the previous table and we can pull out this equation for calculating the uncertainty when we multiply two numbers that have an uncertainty. Okay, now we have the uncertainty of that product, BC. The next thing we see is an addition, A plus the product that we just calculated. Well, we can go to the table and look at how to propagate uncertainty through an addition, and here's the equation for that. And we can calculate the uncertainty of that addition. Then the very last thing, we have the natural log of that addition. We can go to the table, we can calculate the uncertainty, and here's how we calculate the uncertainty of the natural log. So given that table, which has pretty much all of the common things, we can go one step at a time and calculate the uncertainty of much more complicated calculations. And if something wasn't on that table, then you have to resort back to the equation 2 slides ago and derive your own equation for uncertainty. Nothing like some examples to bring this home. Okay, so we have two parameters, X and Y. Each of those have uncertainties. We're adding them together. What is the uncertainty of those two quantities? Let's actually derive this. So the solution is we go back to our main equation for calculating the uncertainty. And here's our general equation. We want to do this for addition. So our function here is X plus Y. So we will replace F in our equation for the uncertainty with X plus Y. So we just go ahead and plug that in. Then we can perform the derivative operation, and we simply get ones here. And so we get the uncertainty in F squared is the uncertainty in X squared plus the uncertainty in Y squared. And sometimes I just like to write it that way. Other times I'll take the square root on the right side. And so our uncertainty in F is the square root of the sum of the squares of the uncertainties for X and Y. And it would be this equation that would go into the table as the uncertainty associated with addition. Second example, in electrical engineering, we use decibels all the time. So what's the uncertainty of a decibel quantity? So we have a linear quantity with some uncertainty, and then we're going to express that in decibels. How do we do that? Well, here's the solution. We apply the original definition of uncertainty. In this case, our function is 10 log base 10 of X. So we'll replace our function over here with 10 log 10 of x. We'll then calculate the derivative of that. 10's a constant, comes to the outside, so we're just applying the derivative to the log function, which of course is 1 over x times 1 over log 10. So we have our uncertainty in f squared equals the uncertainty in x times 10 over x natural log 10, and all of that being squared. And so we have some numbers here that we can actually plug in. And that evaluates to about 4.3 uncertainty in x divided by x. And this would be something that we could put in the table. Now let's actually put numbers to this. Suppose we have a communication system and it has some signal to noise ratio that is 50, plus or minus 1.2. Question is, what is the signal to noise ratio in decibels along with the uncertainty of the decibel quantity? Well, we just derived an equation for doing that on the previous slide. And so we'll apply that to calculate the uncertainty. But first, we'll just calculate the number. So we plug in our 50, 10 log 10 of 50, 16.99 dB for the signal to noise ratio. Now the uncertainty. We'll take the equation from the previous slide, and our uncertainty in x was 1.2. The value of x we just calculated was 50, and we get 0.1. We're not done. Don't box the 0.1. We have to report the final answer, which is the number we calculated plus or minus the uncertainty we just calculated. So the final answer is 16.99 plus or minus 0.1 dB. Here's another great example. Let's say we have a person and we measured him at 6 feet, plus or minus 0.1 feet. Not such a great measurement system, I guess. Then along comes a lady standing on his head, and we measure her at 5.5 feet tall, plus or minus that same 0.1 feet, probably because we used the same measurement technique, which is not a very good one, evidently, to be off by 0.1 feet. So the question is, all right, she's standing on his head. What's the total height of the two, and what's the uncertainty of that total height? And if we didn't know anything about this, we probably would think, oh, the uncertainty is either like 0.1 or 0.2, and no, it's not actually either of those. Well, the overall height is the sum of their heights. It's 11.5 feet, but that 11.5 feet could be off. That has an uncertainty associated with it. And what we have here is the uncertainty of the sum of two quantities. And when we plug in our numbers, we get 0.14 feet. So that's the uncertainty of their total height of 11.5 feet. So we would report that answer as 11.5 plus or minus 0.14 feet. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.